Electron configuration and periodic trends. When we look at electron structure, there's a lot it can tell us about the elements. One thing it can tell us is something about their magnetic attraction, something about how they're affected in a magnetic field. There are two terms that are important. We've got diamagnetic and paramagnetic. Diamagnetic simply means that the substances are not attracted by a magnet, that's kind of repelled by them a little bit. And paramagnetic substances are ones that are attracted to a magnetic field. And it has to do with these regions of spinning electrons in the elements. If you can have regions where those electrons are all spinning in the same direction, you can think of it as concentrating the field, so you get a magnetic substance. But in substances where all of the electrons are all paired up and there are no concentration of electrons spinning in the same direction, then you're not going to get that magnetic field. For instance, if you had something like this in a diamagnetic substance, you would have a situation where no matter what kind of substance, or whether it had sps or ds, every single orbital is spin paired. Every single orbital has 2 electrons in it. So those substances are going to be diamagnetic. They are not going to be attracted by a magnet. Paramagnetic substances, however, in a paramagnetic substance, it doesn't matter how many unpaired electrons there are. If there's even one unpaired electron, it's going to be paramagnetic. It's going to be able to be attracted by a magnet. It could have 1, it could have 3 unpaired electrons. It doesn't matter. If there's even 1 unpaired electron, it's going to be attracted by a magnet. Ferromagnetic substances, on the other hand, are substances that if you remove them from a magnetic field, they'll stay magnetic. So iron is a good example of one of those. Now, when we deal with periodic trends, there are 4 different characteristics of atoms that we're going to look at and see how you can compare atoms based on their location on the periodic chart. We're going to look at atomic radius, we're going to look at ionization energy, electronegativity, and electron affinity. And just by the location of the elements on the periodic table, you're going to be able to tell something about how they are, what those characteristics are relative to each other. So in order to do that, in Chem 1, we use the little mnemonic device focus on fluorine. So if you look at your periodic table, what that essentially means is that as you're going across the table and up the table, this corner of the table is where you're going to get the small size. Because fluorine is little, but it's strong, energetic. So it's going to be a small size, but in everything else it's going to be high. It's going to have a high ionization energy. It's going to have a high electronegativity. And it's going to have a high, more negative, higher energy given off value for electron affinity. So that's our small size but high energy corner of the periodic table. On the other side, we're going to get, as we move down the table and as we move to the left, we're going to get our larger size, but we're going to get our low ionization energy. We're going to get our low electronegativity. We're going to get our low electron affinity over in this corner of the periodic table. So by looking at whether you're moving down the table, across the table, to the right or to the left, going up the table, all of those will help you get relative ideas about how these elements compare to each other. Let's look at atomic radius first. Atomic radius, as we look at our definition over here, atomic radius deals with how big the electron clouds are, essentially. It's half a distance between the nuclei of a molecule that has identical atoms in it. Now, before we can look at explanations for why those trends are the way they are, there are 3 different characteristics or 3 different properties that we need, concepts that we need to know to help explain these. And those 3 begin with nuclear charge. Nuclear charge is simply the total charge of all the protons in the nucleus. And so it's just the atomic number. The more protons you have in the nucleus, the higher the nuclear charge is going to be. Electron shielding and core electrons kind of go hand in hand. Let's look at lithium compared to sodium. So here's going to be lithium. This is going to be sodium. Lithium, if you look at the periodic table, has 2 energy levels of electrons. Sodium has 3. Lithium has 2 in its first energy level, only 1 in the second energy level. Sodium has 2 in the first energy level, 8 in the second energy level, and 1 in that third energy level. Now, if our target electron is this electron in the outside energy level, remember those are our valence electrons, the electrons that are in that outermost energy level, then the electron in lithium, the valence electron in lithium, is going to exhibit a shielding by, or be shielded by 2 core electrons. The core electrons are any electrons that are in a lower energy level than the target electron that we're looking at. So the core electrons for lithium, there are 2. For sodium, if we look at our valence electron in the third energy level, that means all of these electrons in the second and first energy level are considered to be core electrons. And those core electrons, 10 of them for sodium, 2 of them for lithium, shield, we can call it charge blocking. They have this charge blocking effect from these core electrons on that outside valence electron out here. So for our atomic radius, these are the kind of concepts we're going to talk about. One final one deals with Coulomb's law, and Coulomb's law simply says is that this force of attraction is a constant with the charges, some constant, with charges multiplied by each other over the distance squared. We don't usually even worry about what that constant is. We're using this equation to compare. If you notice, if the charges Q1 and Q2 are larger charges, if there's a higher charge there, the force of attraction is going to be greater. If the distance, as that distance increases between those charges, our force is going to decrease. That attractive force is going to decrease. So for atomic radius, we're going to be using all of those concepts to explain why the atomic radius changes the way it does. Now, if you look back at the periodic table, it makes total sense to explain why lithium, that we've already drawn with its electron out here, is smaller than sodium. Lithium has its 1 electron out there in the second energy level, whereas sodium has a 3rd energy level. So as soon as you add a 3rd energy level, as soon as you're going down that periodic table, you're going to automatically get bigger and bigger because you're adding more energy levels of electrons. So that electron cloud is getting bigger and bigger. What's harder to understand is the difference, for instance, between sodium and magnesium. So let's say that this is sodium and this is magnesium now. And so for magnesium, we're going to add some more electrons in here. And on the outer energy level, there are going to be 2 electrons, 2 valence electrons. By looking at it, you would think magnesium would be the bigger atom because it has 12 protons, usually 12 neutrons. Sodium has 11 protons, usually 12 neutrons. So it's got more particles in it. You would think sodium would be bigger. But look at our trend. Our trend says as you go across the periodic table, the size gets smaller. That doesn't really make any intuitive sense if you're thinking about protons and neutrons and electrons as marbles. But remember what's going on here. If we had truly had a nucleus that was the size of this nucleus in here, we would need a football field worth of room or more to scale where that electron cloud would be. The size of the atom is not determined by the particles that are in the nucleus. The size of the atom is determined by how big that electron cloud is. And let's look at the nuclear charge. The nuclear charge is going to be 12 for magnesium. It's only 11 positive charges for nuclear charge for sodium. Keep in mind what Coulomb's law says about a greater charge. When you've got that greater charge, you're going to have a greater force of attraction. And since all those electrons are still in that third energy level for both magnesium and sodium, they both still have only 10 core electrons. So the shielding is no different for the two elements. It's all about the nuclear charge. It's all about Coulomb's law. So that explains why elements moving across or as we move across the table get smaller and smaller, because their number of protons continually increases, their nuclear charge continually gets bigger and bigger. So when we look at an example which is larger calcium or strontium, and you can pause this and write down the stuff that's in red as we go. It just made the notes go faster if I didn't have to write all of that as we went, so I went ahead and pre-wrote that in. But if we're looking at calcium versus strontium, so let me make sure that's right. Yes, calcium versus strontium. Notice that strontium is down here below calcium. It's got an extra energy level. That extra energy level means that strontium is going to be bigger than calcium. So that's why strontium is circled. Now, if we're looking at the difference between sodium and magnesium, that's what we just talked about. We just talked about the fact that since sodium has one less proton in its nucleus, it has a smaller nuclear charge and therefore doesn't attract its electrons as strongly in that third energy level. So magnesium just sucks its electrons in a little bit and makes it smaller in size. Now for ions, positive ions are always smaller than their neutral counterparts. Think about what happens. Positive ions are usually removing all of the electrons, all the valence electrons from that outer shell, which usually means that we've dropped back down into a lower energy level. So we have to keep that in mind for those positive ones. Negative ones, there's another term you ought to be familiar with. It's electron-electron repulsion. As you get more electrons that are added into that same energy level, they're going to have greater repulsions for each other, and they're going to spread out some. And when they spread out, they're going to make the size of that atom bigger. Now, ionization energy. Ionization energy is the energy that it takes to remove an electron from a gaseous atom. So we talk about it in terms of I1, which is the energy to remove the first electron, I2, the energy to remove the second electron, etc. So as you go across the periodic table, that energy required to remove that first electron increases. So as you move across, you're going to get higher and higher energy required to remove the electron. Think about why. Once again, as you move across, you're going to get a greater and greater nuclear charge, which is going to attract those electrons stronger than Coulomb's law, and therefore require more energy to remove them. As you go down the periodic table, Coulomb's law comes into effect again. Think about the fact that as you go down the periodic table, you've got, first of all, more electron shielding. The electrons are further away from the nucleus. If the electrons are further away from the nucleus, they're not going to be attracted as strongly, and it's going to require less energy to remove them. One of my professors once talked about energy rope, and he talked about the fact that if you had two atoms and you were looking at the energy to remove that outside electron, that the higher the energy level for that particular electron, the less energy rope it was going to take. I always imagined this little stick figure guy out here with some rope trying to lasso an electron from an energy level, and depending on which energy level it was in, it would require a different amount of rope, energy rope, to get the electron out. The higher the energy level of the electron, the less rope, the less energy it would require to remove it. If it was in a lower energy level, closer to the nucleus and attracted more strongly, it would require more energy rope, more energy to remove that electron. So we're always going to be talking about where that electron is energy-wise. Is it at a higher energy level? If it is, it's going to require less energy rope, less energy to remove it. So the first ionization energy for fluorine, why is it greater than that of carbon? And as we look at fluorine versus carbon, we see that fluorine has an electron configuration of 1s2, 2s2, 2p5, whereas carbon is 1s2, 2s2, 2p2. Now they both have electrons in that 2p sublevel, but think about it. Fluorine has 9 positive charges in its nucleus. Carbon has 6 positive charges. Coulomb's law again, you've got 9 positive charges pulling on those electrons. They are being attracted more strongly. The more strongly they're attracted, the higher the energy is going to be required to remove them. Why is the first ionization energy for phosphorus lower than that of nitrogen? Look at where phosphorus is. It has electrons in the 3rd energy level. Nitrogen only has electrons in the 2nd energy, its valence electrons. When you're trying to remove that last electron from both of these, you can see that phosphorus, with its higher energy level electron, is going to require less energy rope, less energy to remove it from the atom. Now we get into some that are a little bit different. They kind of, let's take boron and beryllium, for instance. They're the smaller ones. Sometimes it's better to actually draw the structures, because look at what beryllium looks like compared to boron. Here's beryllium with a 1s that has 2 electrons in it and a 2s that has 2 electrons in it. So there's beryllium. Boron, on the other hand, has a 1s with 2 electrons in it, a 2s with 2 electrons in it. It also has a 2p with an electron in it. Now remember our energy rope. Who has the electron that has a higher energy state? This electron right here is in a 2p. It's a slightly higher energy state. So if that's true, it's going to require less energy for boron versus beryllium to remove that electron, less energy rope. So it's all about where that electron is. Now, phosphorus versus sulfur. According to the trend, you would think that sulfur would have a higher, it's further to the right. Look at your periodic table. Sulfur is here, phosphorus is here. According to our general trend, you would think it would be higher in energy, higher in ionization energy than phosphorus for trying to remove that outermost electron. But let's look at where the electron is. Here's the electron for phosphorus. Here's the electron we're trying to remove for sulfur. The outermost energy electron for sulfur is in a slightly higher energy state. Just putting it in, spinning in the opposite direction, with those electron-electron repulsions that are present, is going to put it in a slightly higher energy state. Therefore, it's going to require less energy to remove. It's all about what the energy is, where its energy state is. So look at these 2 examples. We've got the example here where we've got a 1s2, 2s2, 2p6. This one is a 3s1 element. This is a 3s2 element. Which one is going to have the largest I1? Well, the largest I1 is going to be the one that requires the greatest amount of energy wrote, the greatest amount of energy to remove. This one has its last electron in that second energy level. Both of these are in the third energy level. As soon as we find that that 2p is in the second energy, or that ionization energy is in the second energy level compared to the third, more energy is going to be required to remove it. Which one is going to have the smallest ionization energy? The smallest ionization energy, we've got both of the valence electrons in B and C are both at the same energy level. Okay? So they're both in the 3s energy level. But that 3s2 electron is slightly higher in energy. It's being attracted slightly more than the one in B because it has a nucleus that has a higher energy state, or excuse me, has a higher nuclear charge than B does. Since the electron in B then is not being held as strongly, it's going to require less energy to remove. So now we look at a situation where successive electrons are being removed from the atom. We've got I1 here at the top where the first electron is removed from aluminum, and then we continue through removing one electron at a time, and we notice what the ionization energies are at each of those steps. Now think about it. For aluminum, it's a 3p1, doesn't require to remove too much energy to remove that 3p1 electron. Remember, it's higher in energy than the 3s, so it's going to require, in this case, only 80 kilojoules per mole to remove that. So now we look at the explanation for the very large value for I4. So think about which electron is being removed for I4. All of the first three electrons, the P1 and both of the S2s, are being removed with, increasing amounts of energy, because remember, your nuclear charge doesn't change. But as each electron is successively removed, it takes a little bit more energy to remove the next one. But we have a huge increase for I4, but look at what's happening. You're taking away a core electron now. You're moving all the way down to the second energy level. That's a huge decrease in energy state, and therefore your energy rope to remove it is going to be a whole lot greater. So it being attracted so much more strongly, being in the second energy level, is going to require to have more energy to remove. Now, electron affinity is the energy absorbed when an electron is added to a gaseous atom. By convention, the easier it is to add an electron, the more negative the value for electron affinity. So remember, you're talking about energy being given off. So the negative doesn't really matter. It's how big that negative is that we're talking about. So it's more negative as you move across because they're attracting electrons more strongly. Remember, you're getting a bigger and bigger nuclear charge. The constant electron shielding, that's not really changing. Now, as you move down the periodic table, it becomes less negative because you're getting, it's a lower amount of electron affinity because those electrons are moving further and further away from the nucleus. And so it's going to not have as big of an energy change to get an electron put into one of those energy levels further out from the nucleus. So that's the kind of thing you've got to think about for electron affinity. Now for electronegativity is a tendency of an atom to attract shared electrons to itself. It's the same situation. When we focus on fluorine, we're going to get a stronger attraction of electrons when those atoms are smaller. As you're moving across the table and getting more and more nuclear charge, you're getting a greater and greater force of attraction, and your electronegativity is going to increase. As you move down the table, those valence electrons are getting further and further away from the nucleus. They are not as attracted as strongly, and therefore your electronegativity is going to be lower. So which of the following is going to have a higher electronegativity value, carbon or nitrogen? And we look at carbon and nitrogen on the periodic table. We see them here. And since nitrogen is further to the right, remember that means that nitrogen has a nuclear charge of 7, carbon has a nuclear charge of 6, we're going to have the same amount of shielding there, that those outside electrons are in the same energy level, the second energy level, but since the nuclear charge is higher for nitrogen, the valence electrons are going to be attracted more strongly. So it's got a higher electronegativity. Now if we're looking at the difference between sodium and potassium, there's a huge difference in distance for those outside electrons. Sodium and potassium, sodium has 3 energy levels, potassium has 4. So that third energy level for sodium is going to be closer, that valence electron in the third energy level is going to be closer than it is for potassium. Let's just draw that really quick as a quick visual. There's potassium, there's sodium. With that distance away from the nucleus, Coulomb's law, remember Coulomb's law says the attractive force is not going to be as great for the electron in that fourth energy level out here as it is for the third energy level in sodium. So sodium's going to have that higher electronegativity, the higher, stronger attractive force for those electrons.